Okay, let's take a look for volume of a cylinder. Now, we talked a little bit already about how a cylinder and a prism are very, very similar. Here's a prism. It has a length, a width, and a height. It's a prism. It has sides that are a rectangle. So something that I don't know that I mentioned last video, a prism has sides that are quadrilaterals in this case, okay? So that's a prism, whether it's oblique or whether it's right. They're still quadrilaterals. They'd be rectangles if they are a right prism. Now, a cylinder, in this case, is round. It has one round edge, and then it has two circular faces. So, for a cylinder, you have volume equals, and because the base times height is always our reason, volume equals, the base is pi r squared. And so I simply take pi r squared times h. Now we talked about how if you have the radius of the circle, and so pi is approximately 3.14, and you take times radius squared, that's the area of one circle, and you multiply it by height. So you would have something like this, radius, and you'd have to be given some sort of height. And there you go. In our case, I have a radius. Well, let's see here. My actual dimension all the way across, my diameter equals 1 1/4 inches. So my radius would be half that. That would be, instead of 1 1/4, that would be approximately 5/4. Okay. Radius would be half of 5/4, which is 5/8. So my radius on this end should be approximately 5/8 if I marked it correctly. And it is. It's 5/8 exactly. So we have 5/8 of an inch times the height, and that height in this case is 2 3/4, so 2.75. And so what I can do is I can say pi 5/8 squared times 2 3/4, or 2 7/8. So I take 5/8, that'd be pi times 25/64 times 2 3/4, and start putting all that stuff together. So here we go. If I want to do an estimate, I could use 3.14 times 25 equals, divided by 64 equals, times 2.75, and I would come up with 3.37 inches. And that's inches cubed, because remember, whether it's in this shape or whether it's in this shape, it all is a matter of how much material is in each piece, okay? In the same way, we could do the same deal we did last time, and we can do displacement again. And in fact, it'll be a little easier to do displacement on this one. So I have somewhere around 600 milliliters of water because I got my blocks wet last time. And so if I put this in and I push it down to where it is just covered by the water, it goes up to about 650 milliliters. Now let's make sure it's not below 650 milliliters. So our approximate volume would be about 50 milliliters. Now, had I measured in cubic centimeters, we could have come up with a combination and said, yes, in fact, it is. But we'll see how all that goes. Now, we did it by displacement just like last time. So any cylinder is nothing more than base times height, which is pi r squared times h. Pi r squared times h. Now, let's do a different type of visualization. Here we go. Here's off my laundry cabinet. And so I'll take the button and the wrapper, and I'll keep those. And in fact, I only want quarters in this case. Let's just do quarters. Everything else goes back in the laundry money. which is pretty much how laundry money always works. So here we go. I could have a bunch more quarters, but I think that's about as many quarters as I'm going to need. So why am I using the quarters? Well, each one of these in essence is just a circle, but you'll notice even this circle has a certain amount of height. And if I start stacking these circles up, I really start to get some height. In fact, if I went to the bank, I could get wrappers that allow me to take all these quarters and start stacking these quarters into wrappers and rolls of quarters. And that's what you would see in a drawer for changing money. But in this case, I can just go ahead and stack all these dudes up. And now I have a very nice cylinder. If I can get it nice and straight, there we go. That is a nice cylinder. It has a height, has a base, and so all I need to do is I need to measure the radius. So I have a quarter. I suppose I could go to the internet and look this up. For my ease of use, let's assume that the width on this quarter is 1 inch. So if the diameter of the quarters, if the diameters of the quarter is 1 inch, then that means that the radius is therefore 1/2 inch. Now the height of this, let's figure out what the height is. I don't know what the standard quarter height is, but I could, if I knew the standard height of a quarter, just measure by how many quarters. But putting them together, I come up with 1 1/8 inch. 1 1/8 inch. So I come up with 1 1/8 inches. So all I have to do is I say pi r squared h. R is 0.5 inches. Height is 1 1/8, which is 1.125. Okay, and I can grab my calculator and I can say clear. I can say 3.14 times 0.5 squared times 1.125. And I get 0.883. And that would be inches cubed. So how many cubic inches is it? It wouldn't be quite 1 cubic inch, even though it's slightly taller than an inch. Okay, it's an inch across, but because it's not a cube and perfectly 1 inch, 1 inch, 1 inch, you don't have all of it. So you have all of this. Now you say, well, let's find the volume of that. Well, that becomes super easy with displacement because these are metal and they sink. So drop them in, and what you'll find is that our distance or our dimension has gone up, but it's only gone up by about a quarter of the way to the 50. So it's going to be approximately 25 milliliters. In fact, it may not even went up quite that much. Because if I take a look up here, if 3 inches cubed is about 50 milliliters, then 0.88 should only be about a third of that. So maybe we're even a little less than that. Okay. Now, by the way, the quarters also prove another process. Regardless of whether the quarters are stacked up under the water in a nice pretty cylinder, or whether the quarters are laying all over the ground like it's buried treasure or like it's treasure in a treasure chest, it doesn't make a difference. They're going to displace the exact same amount of water regardless of how they're sitting in the water. This becomes an important concept in geometry because whether they are a perfectly straight up stack for cylinder or whether they're scattered all over the bottom, the amount that the water went up stays exactly the same. So whether they're stacked up in a nice straight thing or whether they're knocked all over, it doesn't make a difference on how much volume they take up. This becomes important when we take them back out, because remember our discussion a minute ago about right prisms and oblique prisms. Now, these two are not the same height, but if I had exactly the same height in the cylinder as I had in the oblique prism, we would have the same amount of volume between the two items. And the reason is, actually I'll choose some dry ones. The reason is, whether I take the coins and I stack them perfectly up, we just discussed that they take the same amount of water, whether they're stacked up or whether they're scattered along the bottom of the measuring glass. So in the same way, regardless of whether they are stacked up in a nice pretty cylinder like this, or whether they're leaning over in an oblique cylinder. Let's see if I can make it nice and oblique here. Well, here, I have a solution. There. Now they're a perfectly oblique cylinder. Whether they're oblique or whether they are straight up, they still take up the same amount of volume. And so the same formula applies if I have a cylinder that looks like this. In this case, as long as the radius stays the same and the height from the table stays the same, the volumes are all going to stay the same. So it's always going to be volume equals base times height, volume equals pi r squared h. So there we go, straight up or not straight up, same volume.